Okay, so today I'd like to talk about the Paleo Detector. This project is motivated by the search for the kind of exotic particles and new physics for their fossil damage tracking and ancient materials. Okay. So first of all, let's start from the background. First of all, research is mainly studying using the nuclear immersion. Especially I developed a new very high spatial superfine grain nuclear immersion, very high spatial resolution. The immersion device is motivated by the directional sensitive dark matter search and development of the radio technology for nanometric detection. Because, for example, the case of the WIMPSAT, this track, maybe you know, the energy is very low, so several kV, 10 kV. Track length is very short, so it's in the solid detectors and about the nanometer scale. It's device is capable of detecting the nanometric scale track. Okay, the project is a NEWSdm experiment now, in promoting in the Gran Sasso laboratory. And also, in parallel, now we're interested in, for example, the neutron measurement and any other medical application for heavy ion therapy, using this technology. And also, as my curiosities and radiation affecting materials is interesting for me. This is important for also this Paleo detector experiment. Okay, and I joined the neutron physics experiments. When I was a graduate student, I joined the open experiments. And open experiment is a neutron oscillation experiment. The appearance experiment. Detecting for detection of the tau neutron directly. By immersion detector. Okay, today, today's talk, the Paleo Detector, project, is a new project. And now, we just started R&D. We are doing the several R&D, and also the calibration of the mineral. Okay, this is a the collaboration, is like this. And the Toho University and the Naka University and the Pennsylvania State University and Kyoto University and recently joined the Toho University, for the X-ray, microscope. And also, there are many technical and theoretical contributors. Okay, first of all, what is the Paleo Detector? Paleo Detector is the kind of nature, the materials, and the minerals. The studies, the trace of the cosmic rays. This is motivated by the studying trace of the cosmic rays, preserved in the geological samples over geological timescale. This geological timescale is very important for this the concept. And also the geological materials intrinsically record the phenomena induced by the rare astrophysical event. By studying these records, we can obtain a unique information that cannot be accessed through the artificial experiment. Actually, there are many approaches for Paleo detectors when using the nature, the natural materials, such as for example ice core on the ancient tree and also asteroid and so on. However, the current approach dedicated to the radiochemical and component analysis. In this work we want to add the new information. This means we want to use the tracking technology. And here, I want to because I want to focus on the tracking ability of the minerals. Okay, actually, in the various minerals, working as the tracking detector. Okay, so and for example, so there are many the minerals. So which has the capability of the detection of the track. So such as the halite and olivine and moscovite micas and then so on. Okay, so this is examples of the microscope image. Then actually, so when you see the tracks by optical microscope, so you need a chemical etching. Then after chemical etching, then you can see a clear track like this. So and this track is the fission track. So the fission track mean this is the spontaneous fission track of the uranium-238. So and it's actually so in uranium-238, so and the decay to the barium and krypton, so and very heavier so the decay. So and so back to back. So and this track is the liquid around like this. Okay, so and actually, so for example, by using this track measurement, so and in the geological science, and like the tracks, we utilize the dating method. So and it's called fission track dating. And so like the recording, so recorded information. So as a fossil track, so it's that has age of the for zero around 1 gigayear. So and also this tracks with so which is a consists of the crystal damage, so can be created by high ionization radiation such as heavy ion. Okay, so this detection principle so is so explain later. Okay, so this important point for this paleo detection concept. So so then here, so I show okay, so and here, so I like to discuss about the rare event search. So in the case of the rare event search, so and we need so it's so important to the understand the number of signals. Okay, so and actually, so the number of signal, so is it so proportion, so depends so on the fast and the event rate and the flux so of the particles. So and so in those particles and also to improve the sensitivity, so and we have to so large exposure. So and large exposure, so and define the detector scale and also the time scale, exposure time. Okay, so and so in the case of the artificial detector case, so to improve the sensitivity, so finally, so you have to prepare the very large so mass or scale so detector. So but so in this concept, so paleo detector concept is the focus on the exposure time. So in the case of the for example, the case of the 1 gram the minerals, so and case, so and typically, so like this the minerals has the age of the 1 gigayear scale. So and then so finally, so an exposure, so it's about the achieve the 1,000-ton year scale. So and this is a very so important point. So that's so the most important point is the 1 gigayear scale is very interesting for the history of the galaxy. So and because so and I mentioned that the minerals has a typical age of the 1 gigayear scale. So and then the one cycle of the solar system, so revolution, so the Milky Galaxy is about the 250 million years, 0.25 year. So and if so like the mineral also has a 1 gigayear scale age, then so and so like the minerals, so already they experience the full lap so of the revolution of the Milky Galaxy. So during this cycle, so and maybe so we can expect several so interesting so phenomena. The first of all, so the dark matter case. And actually, so so dark matter distributed around the dark matter halo. So, probably so in right the dark matter halo so dark matter density so is not so uniform inside of the Milky Way. So the dark matter, so the halo. So and we expect the sub-halo components exist so inside of the dark matter halo. So and perhaps like the Milky Way, the minerals so include such information. And also, and so inside of the Milky Galaxy, so there are several interesting astrophysical events. So, and for example, the supernova and the neutron star merger. So that's when such the interesting astrophysical event is very rare. So, for example, the case of the supernova, this rate is about 1 event per 100 years in the Milky Way galaxy. So, and also when the neutrons are matter, so this is a very, very rare. So in the Milky Way galaxies, and this rate is about 1 event per 0.1 mega year. So it's very, very rare. So and it's very, very, very hard so directly observed by artificial detector. So and then so this is the Paleo Detector has a good advantage. So to obtain the information from such rare the events so in the Milky Way galaxy. Okay, so and actually, so and such the particle detector experiment is not so new concept. So and actually there are the long history, and so this is an example. So and about so half of a century ago, and so the regular paleo detector experiment was already exist. So for example, around 1970, by using the lunar rock or the meteorite, so they try to study about the galactic cosmic ray elements. So for example, the analyze the track, from the solar flare, and also by using a meteorite. So they study, analyze the track, due to the galactic cosmic ray element. So especially the very heavier galactic cosmic ray element. Okay, so and from the such starting, this study, they understand for example, the environment of the moon, surface of our solar system history, and through the information from the track analysis. So, and also, so there is an interesting report by the Price and Fletcher. So I did this paper. So in this, they try to observe, analyze the track. So in the pigeon night. And bring back from the moon. So by the Apollo project. So they observed the very long track. Observed. This track length is more than 1 millimeter. Actually, this 1 millimeter scale track is a very, very long, and it's very rare the track. If this track is assume the ultra heavy element, then the atomic number should be the more than 80 or 90, and the energy should be more than 100 MeV per nucleon. From the track length. So actually, such a very element, the heavy element is a very rare event. It's very important the results. And perhaps if this track is at least track length is more than 1 millimeter. So and if this track is more longer than that, might be something the exotic particle such as the multiple emissions.
So how do you know this number from a track length or the kind of a width of a track?
So track length and the detection threshold of the rock itself. Yeah. So this means the DDX. Okay. So other topics, and for example, by the price, and this by this paper, molecular science has what is done, and this society utilize the Moscovite mica. This mineral I will also explain details of my later. This the Moscovite mica is very unique structure. Like it's the kind of military structure. Very thin layers when the start from like this. Tracks and we go to the top layer and bottom layer. By connect this track, by layer, long track, reconstructed. By long-term microscope analysis. By using this technique, try to search the long track search. Assuming the monopole. By using this, the Moscovite mica, they achieve the very high sensitivity, and very strict the flux limit is just shown like this. Okay, so and yeah, so this result is you can see the particle data groups. Okay, so and so this summary of the history of the Paleo detector, so mineral tracking detector. Then I already mentioned from 1960s and 1919. So in this period, so right, so Paleo detector experiment is so carried out very actively. And so, however, okay, so and in this era, so and for example, there are several so key persons. So for example, Fletcher and Walker and Price and this the masters, so and a very important person for these activities in this era. So but from the 19, so and the rate of the 1990 and then, so right is the activity is mostly the slowdown or stop. So maybe I guess that this era, so and the main topic of this field is so shifted to the, for example, nuclear physics and direct detection and accelerator, so such as the Higgs such and so on. So and then like the technique is yeah, the activity, so and slow down. And also I guess that in this era, so this key person so retired, so and this technique so they had not take over. So yeah. And however, so when research around 2020, so when there was movement, so revisit this mineral detector, so the Paleo detector. Okay, so and for example, from the at 2019, so when the several theorists so and proposed the revisit so the Paleo detector so and for the neutron detection and the darkness detection. So after that, so the experimental side, so and we try to so we started to start the R&D, so of the Paleo detector, yeah, and also around 20 so 20, okay, so in 2023, so and we established the international consortium of the consortium so of the for Paleo detectors, so and we published a white paper. So yeah. So and also we held on the workshop. So and every year. So and last week, this workshops I had on in Japan, and also in this year. So and because in this week, so in the workshop, so I had on and so Germany. So and from tomorrow, so I will join this workshop. Okay, so and up next, and I move to the details of the spiral detector. So and first, and I'd like to explain about the track detection principle in the minerals. Okay, first of all, okay, so and this the mineral so detector. So okay, so first of all, so and so this the detector so observe the damage track so in the minerals. So and to create the damage, so and we need the very high energy deposition. So and then actually the typical environmental radiation and the high energy particles, so it's so insensitive to such the particles. So and then the yeah, so the typically so and so Paleo detector sensitive to the DDX more than around the 10 MeV per megagram per square centimeter. So and it's very, very high ionization particles. So yeah, so and for example, this right figure so in this previous search for the calibration of the detection performance in Moscow DMICA. So and for example, okay, so and this is a DDX. So and respect to the velocity. So and this graph point is the event, the confirmed event, so the track formation. So and this the broken so point so is not confirmed the track formation. So and then yeah. So the detection threshold the seems 510 maybe per million switch meter. So and for the Moscow marker. Okay, so and this performance, so and we already we already cross-check by ourselves, so and in part independently. So and this is our result. So and yeah, so okay, by using the ion beam, so on ion beam, so and you can see the right track. So yeah, the factory. So the Moscow maker, and so we can check the so we can check the possible DDX value. So yeah. So and the final result and so the track formation threshold was compatible so consistent with the previous study. So it's yeah. So I don't understand with the American method. Then we can understand the detection performance of this Moscow mine.
Can I ask a question?
Yeah.
How much variation do you have in the DDX? Mineral with the same. I mean, in the same.
Yeah, actually, there's variation. Yeah. Yeah, Michael. So, and I will show later about the olivine. So, in the olivine case, this threshold is a bit higher than that. So, and actually, so depends on this threshold that depends on the minerals. And so we have to calibrate so each materials.
I have just a quick question. It only works with the semi-transparent minerals, right? If you are only using optical microscope to measure it, or what do you use to measure to observe these tracks?
Okay, so this is so check by optical microscope.
Okay.
Yeah. So and after chemical retching, yeah. So actually, this value is varies and it depends on the etching. So condition.
It doesn't need to be transparent, right? That's your question.
Well, I would assume that to get this precision, you need to go optical, but you might go for ultrasounds for deeper. Otherwise, it's destructive, right? It needs to be destructive.
Yeah. So, so when is it? Yeah. So when we see this drugs and so in this very transparency, and it's easy to see them by so the standard of the microscope.
So it's transparent.
Yeah, not transparent. Yeah.
So and then you need to slice.
No,
you don't need.
You just change the focal point. I guess.
Okay. So today, I bring the sample. Yeah.
Oh.
Yeah. Okay. So I will show. Okay. So this is the Toho mica.
Oh. So this is you can just slice, or I mean, how do you get this thing?
Yeah. So this is So you just have the cleavage. Yeah. So and it's easy to take off the thin layer.
Can I take a picture?
Yeah. Sure.
Full scale.
My fingers are not like good for scaling.
Okay, so please.
Oh, yeah. Be careful, otherwise I will need to pay.
But it's very cheap. So it's easy. Okay, so this is a more detailed track formation mechanism in the minerals. So first of all, the high ionized particle pass through the crystal. The division along the trajectory of the charged particle is locally heated to the high temperature. So leading to the melting of the crystals. So this part is the structure. So the change to the amorphous structure. So the molten region is rapidly cooled by the temperature difference with the surrounding medium. So leading to the formation of the lattice defect and the damage track. So amorphous structure. Okay, the structures can be observed by the electron microscope. So this is my observation. So by electron microscope. So this is the cross section. Okay, so this mineral is the olivine. So this cross section view. So the the xenon ions, so and expose from the right, and the thin line, so and this line is so track, and
these strips, these lines there.
yeah, put it the track, yeah. Okay, so and when you see the more detail, so and in the top from the top view, so and so this, so and like this, so and here, so in the spot of the ion, so and this around here, so and the structure has amorphous, so just like this. Okay, so very roughly, my calculation, so and when the regular ions pass through the crystal, so and then in locally, so and the temperature, so that should be the increase to the around 8,000 calorie. So and so usually so the melting temperatures are around 2,000 Kelvin. So and then by the pass through the very high energy particles, and the temperatures will heat up to the 8,000 Kelvin in this local region. Yeah, so and by this effect, so and so damage struck, so created by that. Okay, so and however, so and actually it's possible so to observe by electron microscope. So but the electron microscope is a very so sample structure is very strict. So and it's very difficult so to use for rare events, and because we need the large area the analysis, so scanning. So and then so we want to use the optical microscope. So and to use optical microscope, so and this track how to treat the chemical etching. So by chemical etching, so this amorphous structures and selectively so dissolve, so and also the expanded, and finally so and this track, so the track, so the formed like the tube or hole, so like this. So and finally, so you can see the tracks by optical microscope like this. Okay, so and so discussion. So and this so yeah so and this model also called the thermal spike model. So and so this model is applicable so only to the Swiss heavier ions, high velocity heavy ions. So and this is so just an ionization process. So however, the case of for example, the dark matter search. So when we consider the dark matter search, so and the dark matter velocity is a very low velocity, so around the 10 to minus third, so to light speed. So and actually, so an energy loss mechanism is quite different. So from the swift heavy ion. So and the case of the low velocity case and the dark matter detection case and okay, so this is energy loss mechanism. So when blue is electron swapping power, so the red is nuclear swapping power. So in the case of the velocity of the 10 to minus third, so here, so then the energy loss mechanism, so it's divided the nuclear swapping power and the electron swapping power. So and in this region, so the nuclear swapping power is the largest electron swapping power. Then the track formation, so track formation is contributed to by the nuclear swapping power. So nuclear swapping power is corresponding to the elastic collision of the nuclei and the cascade collisions of the atomic collision. So and essentially, so in the track formation, the process is it should be different from the ionization process. So and the track formation, the model, so it's not the applicable the thermal spike model. So and however, so this non-trivial effect might be so occurred for the track formation for the low velocity region. Okay, so in right, this track formation model and now is under the discussion. Okay, so and the next and the fifth target, so for the Paleo detector. Okay, and now so we are discussing so about the such target and the first and so it's better to divide the minerals from the earth and the space. So and the case of the minerals in the earth, and then so fifth target so should be the first in the dark matter, and also the kind of dark matter, so and ultra heavy exotic particles and qubits and quark matter and so on. So and recently, and there are many theoretical idea. So and such as the cosmic war and another so in the proton decay and so on. So and but yeah. And also the minerals in the space, and this is the target, so should be the galactic cosmic ray element, and also the high charge exotic the matter, and such as strange quark matter. Okay, then first of all, when I directed this, so discussed about the minerals in the Earth, so and then the candidate minerals, so so there are several candidate minerals, but so most of it is mica. So the should be the bed. So because actually so there's the study so using the halide and the zirconium. So in the case of the halide, so and it's possible to detect the track. So and it has the represent the character. So and this means that it's very hard to handle that. And also so zircon. So zirconium. So and this is all this also the good tracking detector. So usually so in the zircon so include a very high uranium contamination. So and then the most of it mica so should be so currently it's in the best detector.
So the uranium contamination is bad for making many tracks by itself.
Yeah. So and I showed the previous slide. So and the fission track. So and the better many fission tracks.
Too many tracks.
Yeah, too many. Yeah. Okay, so Moscovite mica. So I show so this one, So this the Moscovite mica. So and it's so this Moscovite mica structure is like this. So and it's a structure. So and this consists of the like very thin layers and with 1 nanometer. So and so each layer the connect so with a 100 watts force and a very weak force. So and then so it's easy to take So and like I said, so it's easy. It's a clear base, and so very easy handle, and also it's easy to prepare the large area, the samples, and also good transparency. So and so it's very good. So advantage for the optical microscope so readout. And also the good structure formation ability and the etching response is very good. So and this sample is very good for the particle detection. Okay, first of all, so and our the curiosity is first in the dark matter, and then that now so we don't know what is dark matter. So and now so there are many discussions about what is dark matter, and also the mass parameter region is very wide. So and however, so for the Paleo Detector target is a heavier the dark matter. And first of all, so and there is the activity for the WIMP search. So and this is the DMICA project. So and this the project so promoted by the Hirose-san, the Jamstack so scientist so in Japan. So and however, and this week search so the pioneer so the WIMP search by the Paleo Detector is the Snowden et al. And at 1995. So and in this era, so WIMP search by the MICA. So this one. So and by using the MICA, so and the WIMP search already done. So in this paper, so at 1995. Okay, so and in the case of the WIMP search, so and so track is very short. So and so it's so hard to see the track so in the micro. So and then so in this study, so the observed just one the very short pit, so H pit, and then actually actually there are many backgrounds. So and this background is the alpha we call it alpha recoil. Okay, so and this one. So this is the main background of the WIMP search. So in the micro. So alpha liquid track mean then so alpha. So for example, the uranium-238 so decay the alpha occurred alpha decay. So and usually so in the alpha rays, so this mica is insensitive to the alpha ray. So but sensitive to this daughter, so the nuclei. So and so this is sensitive. So and then after etching, so and when you see the microscope, so and then you can see the right is the pit. So there are many pit. So and these are the background for the wave search. So and to reject this background, so and then the as ideas of the noise, so and first of all, so and wait, so okay, so in this case, if so, the nuclear vehicles by dark matter or neutrons, so occur here, so and here, so in the case of the alpha the decay and alpha vehicle track, so and then so this structure so and should be different, so between the alpha decay and the nuclear vehicles, so due to the dark matter or neutrons. So and then if so observe this pitch so depth so distribution. So then the case of the alpha vehicles so case and this so this depth distribution the like this so and like this so and the case of the nuclear vehicle so and then the main the distribution is around the very so the smaller the depth region so distributed. So and then so only see that this region so and then the background so and the background alpha decay background so the can be so decreased. Then
So this distribution is coming from a team or something?
so this case the need to for the case for the calibration. Yeah. So and by using this technique, so and the 1995, so and they got the right wave sensitivity. So and so in this area, so and yeah, so actually, so this cross-section is the higher. So but in this area, so and so it was a very good so sensitivity. So actually, so in this case, the target is just the very small, so only nanogram. So only nanogram. So but the because of the long time exposure, so and 0.5 gigayears, and then so and they so achieved such the cross section limit. Okay, so in recent activities, the DMICA project, so in okay, so and that's this readout, so carried out by the AFM, so atomic force microscope. So and however, the atomic force microscope is a very slow scanning. So and so this scale is limited by this the readout. So but now, so and we have the very good, so very high so level the high technique. So and so this Japanese. So and this is the optical profile microscope. So and this is the so resolution is almost the same so with the airframe. So but the readout speed is very high. So high speed, actually high speed. So and by using the touch cut image technology, so and this green touch activity so will be improved. And yeah, so and this is the sensitivity of the DMICA project. So and the case of the 1 ton year the scale. So and then in this case, the main background is the neutron. So neutron. So and okay. So and the finally so and expected sensitivity is so and at least and this sensitivity so will improve the previous work so by the Snowden in 1995. So like this. So however, so unfortunately, it's so hard to achieve the Zen 1 ton, so Zen 1 sensitivity. So, but in this case, the qualitatively, so new method to analyze the data covering more than one full orbit, so in the Milky Way. So and then, so actually, so yeah, so this part detection, so study, so can obtain the new, quite new information. Okay, so and as the next target, so and this is the curiosity. So and I'd like to focus on the composite dark matter, so the heavier dark matter. So because the dark matter density, so local dark matter density is fixed from the rotational velocities of the Milky Way galaxy. So and then the dark matter flux. So this inverse proportion to the dark matter mass. So in the case of the very heavy dark matter, for example, the dark matter mass is 10 to 20 GeV, then the expected dark matter flux on the Earth is the rho of the maximum is 10 to minus 30 pascals per second, so very, very low flux. So and then so it's very hard to search the flux of the artificial detector. So and then the Paleo Detector should have the good advantage for such very low flux events. So and because of the very long time scale, so exposure. So and such a very very heavier dark matter, so it's a unique search. So and so it's still blue ocean. So and so this is the main motivation for our team. Okay, so and for example, the target of our team. So and actually, for the heavier exotic particles, and there's several theoretical motivated exotic particle prediction. So and for example, the cubole or the nuclear light, the strange bulk matter and molybdenum. So in such a the theoretical motivated particle is motivated by, for example, the baryon lepton number generation and supersymmetry and gas and so on. And so such a the very important so top so and so such an important domain subject so motivated so and it so I think that it's important to start to touch the new particles so and with very so ultra heavy so now. Okay, so first of all, then cubole. Then cubole so is a non-topological solid on the scalar field. So and it has a quantum number. So and also by Afric dying mechanism. So this is during the inflation and motion in the phase direction due to the theta dependence. So phase dependence. So and by such mechanism. So and this scalar field that can generate the baryon and lepton number. So this is the kind of the baryogenesis and leptogenesis process. And also, and this cubole, so and like the cubole, so is the kind of the quantum state. So and so this mass, so is expected to have the for example, the mass scale is defined by the cubole mass so per baryon number. So if this cubole mass per baryon number is lighter than proton mass, so and then actually it's a proton, so it's the most stable baryon. So and then this value so is smaller than the proton mass. So and then the cubole so should be very stable. So and the longer than the age of the universe. So and then if the cubole so should be behave the kind of dark matter or the part of the dark matter. Okay, so and now so we as benchmark model, so now so we are considering about the stable charged cubole. So and this model is following the Kawasaki standard. So this is the theoretical group of the University of Tokyo. So in this formalism, so it's like this. So and first of all, so and we assume that the cubole so with both the baryon and lepton charge. So and if the baryon the lepton and the baryon number is equal, so and then the cubole, so the electric charge is neutral. So however, so if some condition, so and this cubole can decay to the electron, so and then this cubole so charge up, so to charge up, so and behave the plus charge the particles. So and our universe and such a charged particles they capture the electrons so and behave like the very heavy atom. So and in this paper so and so discuss about the stable condition of such a charged particle condition. So and so and I don't explain details about the final reason like the cubole so can charge. This decay so will be stopped. So to the maximum rate of 100% and inverse to the fine structure constant. Okay, so and in this mechanism, so and it can make the stable condition so with as a charged cubole state. So and like this, if like this the particles exist in the universe, and then so it's possible so to search by the Paleo Detector.
But it doesn't interact with electromagnetism and with photons and so on. If it has an electron, means we can see in the optical way. No?
So this case, the assuming the very heavy mass, so and then it's very hard to
Rare.
very very rare. So and the number density is very very low. So and it's very hard to observe the telescope. Okay, so and in this case, we can calculate the DDX N0. So and so in here, then I calculate the N0. So and the case of this case the velocity is 10 to minus half. So and then I already mentioned that the nuclear stopping power is the dominant. So for the electron N0. So and to calibrate the performance of the drug formation performance. So we use the ion implant system. So and this the very small the accelerator. So and by using that, so and we can expose the several 10 kV ion, so and heavy ion. So and this is an example of our result. So and by using that, so and I expose the external ion, so 50 kV on the mica. So and this one. So and after etching process, and we observe the atomic force microscope. So and then we could see the clear like this H bit. So right figure is knowing that there's a region. So and the clear reason, so we could see the H bit. So and by this test, so this mica, so sensitive to the such cubal. The particles. If so, such a cubes pass through the mica. So and now, so the more precision efficiency study is ongoing. So that it seems the very high efficiency and the mostly 100%. Okay, so in this case, the 750 kV KT corresponded to the charge of the 40 of the cubes. So and here, so we calibrate around here. So and other the parameter space in now, and we are studying.
Quick question. Yeah, they are on the same scale, right? In terms of dimension, size.
Yes, yeah, same. Yeah. Okay, so and then next is the track length of the charge cube. So and actually, it's such very heavy particles and has very long track length. So and so this is the track length. So respect to the cube mass. So and so track length and can be calculated by the formula. So and they're from the DDX and the physical energy. Okay, so and first of all, in the case of the 10 to minus 30 GeV, then so the charge cube should be able to pass through the 1 kilometer long. So and here, so and it's 10 to minus 30. So and then track length. So in the track length should have the 10 around 1 kilometer. So and then, but usually, so in such the mineral also should have the underground. So and then So this is the lower limit of the surgical mass. So depends on the depth of the mineral in the earth. Okay, so in the case of 1 kilogram rock, so and then the lower limit of the mass is around 10 to 30 GeV. So it's possible so to search the cube, so with more the mass of the more than this value. And for lower mass parameter reasons, and actually, so it's better to use a mineral on the moon or a meteor, right? So and this is now, so we are discussing about that. Okay, so and here, so and I show the expected sensitivity for cube search with the Paleo Detector. And first of all, so as a pioneering the experiments, there's macro experiments. So and this is the artificial detector. So and so it's the carried out in the Gran Sasso laboratory. So here, so and so this macro experiment utilizes the classic damage detector. So and the area is the very large the area, so about the order of the 10 by 10 square meters, and the exposure should be 2 or 3 years maybe. So and finally, so the macro experiment sensitivity was around the flux limit So it's about the 10 to minus fifth per square centimeter per second per Straussian here. So, and if so, we search this sensitivity by this so most of it mica. So and then the 1 square centimeter is enough. So and by just to see the 1 square centimeter, so and this sensitivity so achieved. And so this line is the monopole search limit. So by the Prof of the 1986. So and actually, so this the search is motivated by the monopole search, but so the maybe so the monopole track and the cubal track is almost the same. So and then if so we convert it to the cubal, so from the monopole search, so and then the mica the search with the micas and the achieved sensitivity is around 10 to minus 20 per square centimeter per second Straussian. So and then so this case is the analyzed so area so was about 600 square centimeter. So just the this is the A4 size. Yeah. So and yeah. So and by improve this sensitivity. So and okay, so by using the current cutting edge technology, so and this so sensitivity so will be so improved more, and also by that so and for example we can search the spherical parameter so theoretical parameter space. So in the yeah so the expected from the so theoretical model.
So just the lower limit of the mass is coming from
Yeah. So and yeah, that comes this so depends on the where so yeah minerals so yeah. Okay, so another target is the strange cork matter. So the strange cork matter is the hypothetical state of the matter composed of the up, down, and strange corks. So and there is a proposed as a more stable so form of the matter than ordinary nuclei under certain condition. So and actually, so this strange cork matters in the predicted by the Franz and Witten in 1948, 84. So and so this property is nearly the equal number of the uses quarks, so and it's extremely high density. So and also it can be slightly positive charge, and yeah, and also it's the very stable condition. So and yeah, so and actually it's the various so studies and calculated so by the stable condition. So and there are many the parameter space so become the absolutely stable. So and actually so and when the discuss about the stable condition when so it's the so important parameter is the cubal energy so per this A is a volume number. So this energy per volume number so is smaller than the 930 MeV case. So in this case is the strange cork matter so will be very absolutely stable. So in this value so is the case of the iron nuclei. So because the iron is the most stable so nuclei so in the universe. So then so this value is smaller than iron. So then this cube also is very stable. So and so this stable conditions that can be achieved more than the baryon number. So the cork number is about 10 more than 10 to the third. So and then so this corresponding to the mass is about the TeV or more. So and then so this SQM mass is more than TeV. So and then the SQM so will be very stable. Okay, so and also, and in the case of the strange cork matter, so and this size is depends on the mass. So and because this mass is corresponding to the number of cork, and then so yeah, so this size scale is the depends on the mass. Okay, so and then the case of the mass is more than 10 to the fourth GeV. So and then this mass size is more than the 1 angstrom. So and then so like this, a very heavier SQ when the granular is approaching the macroscopic object. And in this case, when we calculate the DDX, and then the cross section with materials is considered as the geometrical size scale. So and then by using this DDX and here, and we can I calculated the track length, the respect to the mass scale. And actually, so this is also the same so with Q-ball. So and about the 10 to 4, so this is SQM mass is more than 10 to 4 GB. So and then the track length around 1 kilogram, 1 kilometer more. So and then such a Q-ball, so is the one of the target for the Paleo Detector. So, but in this case, the size is larger than Q-ball. For the very large mass scale. So and then maybe it's going to track the forming a track should be very easy. So and yeah. Okay, so and then the expected flux limit of the SQM. So this is the same way the Q-ball. So and yeah. Okay, so and so we improve this sensitivity. So microscope scanning is very important. So and I mentioned the because my background is a nuclear immersion. So and actually it's a nuclear immersion, so using the automatic optical microscope readout system. So and so this is the system. So and for the NEWSdm experiment, and so this is a microscope. So and we can scan the nuclear immersion film, so like automatically. So and actually, right, the system is applicable to the readout, so the Paleo Detector. So and actually the current, so this system is the speed is about 20 hours per 100 square centimeter. So and its speed is it's not so low speed, but if we optimize the Paleo Detector, so it's the speed is will be improved more. So now about maybe it's 1 hour per 100 square centimeter. Then also, and by improving for example the moving stage and the quality of the camera and so on, and then we expect that the speed so it's about improved to around 10 minutes per 100 square centimeter. So then it's easy to improve this sensitivity more. Yeah. So and the RACS technique, optical microscope scanning technique is very important. So and now, so and we are constructing the optical microscope system. So we call the QTS for the Paleo detector, like this. So and so this is the very standard microscope about installed driving stage and the camera. So and this system installed the nuclear immersion system. So and now so this system is constructed already. So and we started the commissioning. And also this image processing have to be optimized to the Paleo detector. So and now so we can starting the image processing system and optimize to the Paleo detector. Yeah. So and as the next topic is the mineral in the space. So and okay, so when we consider about the mineral in space, so and then the target is the galactic cosmic ray element and the high charge particle. So and then actually so this mica so is only in the Earth. So and then when we search when we use the mineral in the space and the good candidate is the olivine. Okay, so the olivine so it's abundant in the meteorite and the lunar surface. So and also and here, so I bring the olivine also, and so this olivine from the bring in the Earth, so and not meteorite, yeah. So very small, Okay, and first of all, then we didn't have the technique, so especially etching technique. So for the olivine, so the first of all, then we try to establish the etching method based on the this is based on the EDTA solution. So and by now, then we already confirmed this etching process, so, and so we became possible to observe the track so in the olivine. Okay, so and by this, so and this also, and by using the ion beam, so and we check the track formation performance. So and okay, so this is the track of the in this case the gold of the 350 MeV. Okay, so and I'm sorry, so and this line in the just the policing mark. So and this is not track, so and this the block, so this. So this is the trouble goal. And this in our calculation, so in this the tracking threshold is about 60 MeV per milligram per square centimeter. So and so this value is a bit higher than the Moscow DMICA. Okay, so this target so is for example supernova and the neutron star major. And the first of all, so and now so we are discussing about the ecliptic particle started from a neutron star major. So and this is also the case of the strange quark matter. And because we expect the neutron star, so in the context of the strange matter, so in the core of the neutron star. So and then the strange quark matter so might be emitted from the neutron star major. So in this case, okay, so and on the long time scale accessible to Paleo Detector, so and then there is a possibility that the neutron star majors occur in the vicinity of the solar system. And for example, this is a rough the calculation. So and assuming the randomly distributed in the Milky Way disk. So and then, for example, the case of the near field range in the 1 kilo parsec. So and then we can expect the 30 times occur in the 1 kilo parsec, so in the 1 giga-year scale. Actually, so in the neutron star major is very, very rare. So, but so in the case of the 1 giga-year scale, so and then, and the several times the neutron star majors occur in the 1 kilo parsec scale. So then it's very interesting. So, and then if like the strange quark matter, so emitted the neutron star major, so and then we try to calculate the weather, so we can detect the neutron such particles. So and for example, this case we are the accelerated energy of the neutron star major is the maximum the 10 to 10 GeV. So and then so kinematically, so and SQ around rather than 10 to 11 GeV, so it can be accelerated to so better about the 0. More than 0.1. And so higher, yeah, so and it's the higher the SQM, so should be able to emit it so from the neutron star major. So and then so this is I try to calculate the energy loss so respect to the beta, and also the actually so the origin threshold about like here. So and then so it's sensitive to the variable number of the higher than 10 to 4th, and this mass is corresponding to the 10 to 4th GeV. And also, and this color is corresponding to track lengths. So in the track lengths around the 10 or 100 centimeters, 1 meter, or yeah, so several 10 centimeter or 1 meter scale. So and so and this track length is possible to pass through the meteorite so scale. So and then it's so such a the accelerated SQM so can be detected so by for example the olivine in the meteorite. And also another target is ultra heavy galactic cosmic ray element. So this is not the particles, but it's very important for the nuclear synthesis in the universe. So and for example the recently so and we already know the nuclear synthesis process in the process. So and especially when our process is important for the very heavier elements, so, such as uranium or transuranium element. So, and the neutron star major is a very important source of the outer process. So, and so recent study, so a neutron star major, so outer process in the neutron star major is very essential. So to created generates very heavier atom in the solar system. So and yeah, okay, so and actually recently, so and very interesting result the published in the so Russian groups. So and this is the Olympia experiment of the Olympia experiment. So and so the groups so it studied the olivine in the meteorite, and by pick up the olivine so in this parasite meteorite. So and then observe the galactic cosmic ray element inside of the meteorite. Okay, so and this important technique of this groups is it's possible to do the charge identification. So and by the etching the measurement of the etching velocity of the rock for each rock. So because of this etching, so the process depends on the dx of the particles. So and then this etching speed, the chemical speed, so is depends on this structure of the here. So and also this velocity depends on the energy loss and the dx of the particles. And this means that by using the etching velocity, so it's possible to identify the charge of the incident particles. So and this group is already calibrated by the heavier ions and the iron, the krypton, xenon, and uranium. So and then this etching velocity is the clearly depends on each atom charge. And also, and maybe the proof is very clear. So, and this is the vertical axis is the etching velocity of the one stopping region. So, and with respect to the charge of the atomic number. So, and this velocity is a very good correlation. So with the charge of the ion. So, and by using the calculation data, so and it's possible to identify the charge of the galactic cosmic element. So from the meteorite. Okay, so this is the result. So the atomic number, the charge spectrum. So and that is also this Olympia experiment. So in the other, the plot is the spectrum. So from the artificial detector, so such as the three-track detector, the scintillator, and so on. Okay, so and Olympia, the case of the Olympia case, and this is the Paleo Detector, so and the time scale, the gigaton scale. This is a very unique point. So and the Olympia, yeah. So and from this result, and they reported the very interesting points. So there's 3 events. So and this event, so the has the charge of the atomic number of the 120. So and it's an unbelievable result. So and because this is the atomic number of the 120 and corresponding to the 1 here. Okay, so and this is so and here, so in the ion stability, so and this value is consistent with the ion stability, so of the nuclear physics. So and ion stability, so is just a theoretical prediction. So and now, so there's no evidence from the experimental side. Yeah, so and but if their result is the truth, and it's it's a very interesting result. So and then how can such a high Z element produce and how those accelerated. So and such a very it's very interesting topics. So actually it's not clear. Yeah, so and we have to do the cross checks about that. So and so this is one of the curiosity for our team. So and now then we are studying about the charge identification, so and with the same techniques of the Olympia experiment. So and we try to cross check their result. So and this is the preliminary result in our by our measurement. So and approximately this is the case with the xenon. So and we try to check the etching velocity respect to the residual range. So and the behavior is also is consistent with the Olympia experiment. And also, and we check the etching velocity around the stopping region, so respect to the charge Z. And so this works. So and as our results. So and the current, so our result is also consistent with the Olympia experiment. So in the next file slide, we have the machine type of the crystal and the iron. So and so this test slide we can using the cross check over the Olympic experiment. So and this is our one of the curiosity. Okay, so and now so, and we are the started to handle the meteorite. So and first of all, and we can get we could get the select sample of the EMIRAC, so meteorite. So this name is the EMIRAC, and found in 1822. So and they found in Atacama, Chile. So and by using this samples and pick up the olivine crystals. So and then we can started to analyze the tracks in the recorded in this olivine. Okay, so and so summary. So Paleo Detector provide a new approach. So to the astrophysical, so astroparticle physics using a natural mineral detector and geological timescale all of the minerals to record the provide so unique information on the history of the Milky Way galaxy. So and it's very important, interesting for the search of the dark matter and the part of the dark matter, so and such exotic particles with ultra high mass and extremely low flux. So and also the measurement of the heavy galactic cosmic ray element and their charge and energy. So it's very so important and there should be new information. So and yeah, so. Yeah, so and for that, so and now so we are starting using the main is and the most copied micros and the origin. Yeah, so and yeah, so pick up the meteorite. Okay, so that's thank you.